So, we start again with the new lecture, that is lecture 24. We will again continue about the structure of ionic solids. In the previous lecture, we looked at structures of fluoride structured compounds basically, and fluoride structured compound basically CaF2 structure or A2X kind of structure, where there is a difference in the coordination of cations and anions because of different valences. So, as a result, your cation is coordinated by 8 anions in CaF2 and anion is coordinated by 4 cations, and converse is true for A2X kind of compound, anti-fluoride structured compounds. And the unit cell as we drew was a little complicated unit cell, but it is not very difficult. I mean, once you draw the top view and from top view you draw the 3D view, it becomes very clear. So, now we will look at the remaining. We started with the spinel structured compounds, which is Ab2O4, but we will look at this in detail. And there are some other cubic structures in which anions are arranged in cubic fashion and cations go to the interstices. They look very similar to FCC in certain cases or BCC in certain cases, but they are not FCC and BCC structure, but they are cubic. So, let us continue discussing our spinel structured materials. So, spinel, as we discussed in the last lecture, there are two variants. One is normal, second is inverse. Both are Ab2O4. In this case, A goes to tetrahedral sites and B goes to octahedral sites. In this case, one of the B goes to tetrahedral sites and A and remaining B go to octahedral sites. We can see that there are now the unit cell in this case is typically made of 8 formula units. So, because to accommodate these interstitial atoms in a regular periodic arrangement so that you can form a lattice. The lattice does not come in one formula unit. You have to put in 8 formula units of Ab2O4 to put these atoms in the interstitial positions in a repeatable manner. Okay. So, the lattice is little bigger. So, one unit cell contains 8 formula units of basically Ab2O4. So, it is a bigger unit cell, and we will see how the structure looks like just in the different slide. So, this is how the structure looks like in case of Ab2. So, now since it has a FCC symmetry, FCC lattice is made by cations and anions both, then only it is a FCC lattice. So, here you can see the lattice is drawn in such a manner, so that lattice corners are put on the A atoms. This is for Ab2O4 normal spinel. So, A atoms occupy the tetrahedral sites, and you can also build FCC lattice based on that, and the B atoms go to octahedral sites, and oxygen basically are the cations, anions. So, this is the tetrahedral coordination where each A atom is surrounded by 4 oxygen atoms, and this is the octahedral coordination, in which in this what will happen is that, so if you have one blue atom there, so if you have one blue atom there, you will have another blue atom here, you will have another blue atom here, and you will have another blue atom here. So, this will make a octahedra, right. All right, you can see that this is my blue atom, this is my blue atom, this is my blue atom. So, all of these are oxygen atoms, right. They make a octahedra, and within these octahedra you have this cation sitting. So, only half of them are filled. So, they are filled in such a fashion so that you can see this is that unit cell, bigger unit cell, and these are all oxygen atoms placed at various locations, and within them you have at some locations A atom, some location B atom. So, this looks very complicated. So, how to comprehend this? Well, you can comprehend this if you look at the structure in a little different manner. So, let us see. So, this is sort of the filling sequence in this structure. So, if you see at Z is equal to 0, I start with the layer of oxygen atoms. These orange one are the oxygen atoms. Okay. Now you can see that there are 4 squares, all right. So this is the bottom half of one unit cell, FCC unit cell. This is bottom half of another FCC unit cell. This is another FCC unit cell. So you can see that you have basically 4 FCC unit cells, right. But this is at Z is equal to 0. You are going to have 8 of these. So 4 on the top, 4 on the bottom, 4 on the bottom, 4 on the top. Now within these you start filling the octahedral sites first. So you can see that this is an octahedral site, edge centers are octahedral sites, right. But you don't fill all of them, you fill only half of them, because octahedral site occupancy is only 50%. So this is octahedral site, you fill. You cannot put them randomly, you have to put them in a fashion so that you end up making a periodic unit cell. So the way it fills it, it turns out 2 atoms go there, 4 atoms go there, this row remains empty, this row remains empty. Okay. The next row at Z is equal to 1 by 8 will be tetrahedral, because now you have 2 unit cells. So that 1 by 4 in normal FCC unit cell becomes 1 by 8, right. So 1 by 8 position is the tetrahedral position. So you put 2 tetrahedral atoms, which is the A atom. So this is these are the octahedral atoms. Okay. These are FCC unit cells. So when you go to Z is equal to 1 by 8, you go to the plane in which tetrahedral interstices are there. So tetrahedral interstices, you fill only 2 of them, you don't fill all of them, because you cannot fill all of them, you have only 1/8 occupancy. So you have filled 2 of these tetrahedral sites in this fashion. Then you go to next layer, which is at Z is equal to 1 by 4, which is the middle part of the next FCC layer, right. So this will become, so this is the bottom part of first FCC layer, this is the middle part of the bottom FCC cell. So you can see that here the atoms were here on the corners and the face center. Now here they have become, so here they have come at the face centers. Okay. So face centers on the sides. So these are all oxygen atoms, and you again fill the octahedral sites in such a fashion. Now you fill the octahedral sites in a rotated fashion. So here they were going all along in this direction, now they have rotated by 90 degrees. So this is the next layer of octahedral atom. So this row is filled, this row is empty, this row is filled, this row is empty, then again this row is filled. Okay. Then you come to Z is equal to 3 by 8, okay, which is the again tetrahedral plane of the bottom half of the FCC unit cell. So again you have filled the first 2 layers here, first layer of tetrahedral site here, now you fill the tetrahedral site here. And then again you go to Z is equal to half. When you go to Z is equal to half, you come at a position which is same as Z is equal to 0, because it stops top surface of the bottom FCC unit cell. So the oxygen atoms are arranged in same fashion. However, the octahedral sites are now filled in different manner. Instead of keeping these empty and these empty, you shift the octahedral sites by another vector in the 110 direction. So you can see that this layer is now empty, this row is filled, this row is empty, and this row is filled. And then again you go to tetrahedral plane, you rotate now the tetrahedral interstices position. Now the tetrahedral sites which are filled are those which are along this axis. Then you go to Z is equal to 3 by 4. Again you go to the similar structure of as you have here, but again you rotate the position of filling. So now the tetrahedral sites are filled, octahedral sites are filled in this fashion. This row is empty, this row is filled, this row is filled, this row is empty, this row is empty. Alternate filling of rows. Finally you come to Z is equal to 7 by 8, where you have filled 2 tetrahedral interstices. Now you can see that these are shifted with respect to what you have at Z equal to 5 by 8. So these are shifted to the next available corner. Then at Z is equal to 1, you will have the arrangement which is same as Z is equal to 0. So this is how you arrange cations and anions, cations in a periodic in 8 FCC unit cells, so as to achieve a unit cell which is periodic in nature, which is repeatable in nature. Okay. So this is a complicated lattice. You have to go layer by layer filling of cations in the anion lattice, and this will make a big unit cell of spinel structured. So this is how it's going to look like when you make. So these are various octahedras stacked up. Octahedras will consist of basically the cations, B cations, and tetrahedral sites will contain the A cations. So this is basically the spinel structure as I was talking. So you can see here this contains 8 unit cells of formula units of AB204. So essentially, if you look at the top view, you're going to have so just like we drew 8 unit cells of fluorine in CaF2 structure, here you again draw the 8 unit cells of oxygen, but they are not cubic cells now, they are FCC cells, and then you fill the interstices in a layered fashion so as to make a periodic structure. So what I showed you just now was a spinel structure compound, and this is of a lot of importance because a lot of engineering oxides such as materials like Fe3O4, NiFe2O4, COFe2O4, all of them they follow basically spinel structure, and these oxides are interesting because they are magnetic oxides and they are called as ferrites. They are used for a lot of magnetic applications. So that is why it's important to know how the sites are filled in these structures, and based on the site filling they show some interesting magnetic phenomena. Okay, so now let's move on to the next structure, which is called as so these are the structures which were based on FCC packing of anions. There are certain structures which look as if there is a BCC or FCC packing of anions, but if you look at the lattice carefully, it's just a simple cubic lattice. So in this category, let's categorize as cubic arrangement of anions. So in this we will look at first perovskite structures. Perovskite is known as AbO3 structured compounds. Then we have ReO3 structured compounds. And then we have CSCl structured compound, cesium chloride. Okay. So let's first begin with the perovskite structured compounds. So in this category, the general formula of these compounds is AbO3, okay, and this is again an ionically bonded solid. The compounds that you can include in this category are things like barium titanate, lead titanate, KNbO3, potassium niobate, calcium titanate, strontium titanate, various titanates, niobates, they follow this kind of structure, and although it's cubic in many circumstances, at least some forms of these oxides are cubic, they tend to sometimes distort and they make non-cubic structures. So they exist in both cubic as well as non-cubic forms. They are slightly distorted from cubic structures. So the way this structure is made is like this. So in this unit cell, the oxygen atoms, if I refer them as orange occupy the face centers of this cube. The barium atom, so let's write the formula, let's say AbO3, okay. So there are 3 oxygen atoms, right? Half, 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 half. So 3 oxygen atoms. Let's say the A atom is the bigger cation, it goes at the cell corners. This is A and this was oxygen, and the B atom is the smaller cation, which is B. So A is typically a large cation such as barium, strontium, lead. B is a small cation such as titanium, okay. In many cases it is titanium, it could be zirconium and iron as well in certain cases, and some other atoms. So you can see here it looks as if it's a FCC structure, but it's not FCC structure because not all the sites, face centered sites, are filled by same atom. So the corner of the cube is occupied by A atom, the face center of the cube is occupied by oxygen atom, and center of the cube is occupied by B atom. So this lattice is basically a cubic lattice P type, that is primitive cubic lattice, okay. It has one formula unit of Ab2O3, A atom being at A at 0, 0, 0, B at and oxygen at you need to define all the positions. If you are defining a primitive lattice, you need to define all the positions because primitive lattice vector is only 1, 0, 0. So if you go from half 0, 0, the lattice translation is only 1, 0, 0, 0. You will go to 1 half, 1 half, 1 half, 0. So you can't get this point. So you need to explicitly mention this point to get this other, because in FCC lattice the lattice vector is half of 0. So you can translate each point by half 0, 0, half of 0, half 0, half, and 0 half half. But in this case the primitive lattice vector is 1 0 0. As a result 1 0 0 or 0 1 0 or 0 0 1. As a result you can't get the other points, okay. So if you translate half of 0, you will get, let's say if you translate half of 0 by 1 0 0, you will get 3 by 2 3 by 2 0, right. If you translate this by 0 1 0, you will get 0 3 by 2, sorry, this will be 0 3 by 2 half 0. Similarly, if you translate this by 0 0 1, you will get half half 1. So you will again reach the same point, you will not reproduce these 2 points. So in order to produce these 2 points, you need to explicitly mention them. So that is why it is a primitive lattice, and it's so now look at the coordination here. B atom is a smaller atom, the coordination of this is 6-fold, which is octahedral. So you can see the octahedra here. This is the octahedra that you make. Okay. So B atom is octahedrally coordinated. What about A atom? How many, if you look at A atom here, let's say this A atom, it has one neighbor here, it is another neighbor there, it is another neighbor there. 3 neighbors are present in this unit cells, and it's going to be surrounded by 8 unit cells, right? It's going to be shared by 8 unit cells. So, but some of these atoms are shared by 2 unit cells, so it will be 12-fold coordination, and it makes sense because B is a smaller atom. It requires, based on the radiation ratio, it has 6-fold coordination, and A has a coordination which is 12-fold because it's a bigger atom. You can represent this unit cell in a different manner also. If you let's say if I put the titanium atom at these corners, let's say this is titanium atom. Now, these are titanium atoms. Where does oxygen go? Oxygen goes to the and where does barium go? The barium goes to the, what is the color barium we used? Red one. Okay, put the red one right here. Now you can see the 12 neighbors, 4 of these, 4 of those, 4 of those, the 12 neighbors to the barium atom. Is that clear? So this is barium, this is oxygen. So this is the structure which is called as perovskite structure. So you can see that this structure is as if you can write the you can mark the octahedras here. So this is the first octahedra. You will have one on the other side. This is another octahedra, and one on this side. And you can connect this octahedra to these points, and the one at the bottom will be here, right? So these are all vertically stacked octahedras. One octahedra here, another here, another here, another here, another here, another here. So you have 8 octahedras vertically stacked up. So this is basically the polyhedral representation of the unit cell. You can also do the bond strength check here. Now cation for barium, barium is, it has a valence of 2, it's surrounded by 12, right? Its bond strength is 6, 1 by 6. Titanium is surrounded by, it has a valence of 4, surrounded by 6, it has a now oxygen has a valence of 2, coordination number, something coordination number. Now either you know the coordination number, you need to get the valence out. So what you can do is that oxygen valence in this case is bond strength of barium multiplied by coordination number of oxygen by barium plus bond strength of titanium multiplied by coordination number of oxygen by titanium. So it turns out you have then the first case 1 by 6, the how many barium atoms around each oxygen atom. Let us say this is the reference oxygen atom, okay. One in this, one on the back, one here, and one here. 4. Bond strength of titanium is 2 by 3. And how many oxygens, how many titanium surround the oxygen atom now? This is oxygen, one on this side, one on that side, only 2, right? Is that right? So this is 4 by 6 plus 4 by 3, which is nothing but 8 by 6. So this becomes 2, and oxygen valence is 2. So it does follow the rule of bond strength, because it gives you the same valence of. So basically solid is electrically neutral. If you get something other than 2, which means there is something wrong with the coordinations, because the valence of cation and ion must electrically, the number of atoms and the way they should be arranged in such a fashion so that solid is electrically neutral. So each of them have that coordination. So this is perovskite structure. There are a lot of compounds which are perovskites. So examples of perovskites is not only you have barium titanate, lead titanate, calcium titanate, etc., strontium titanate. There are various solid solutions. So for example, in these you see barium is +2, titanium is +4, but they don't need to be like that only. There are a lot of other cases. For example, you can see LaTaO3, okay, LiTaO3, lithium tantalate, and then you have LaGaO3, okay, you have BiFeO3, you have LaAlO3. In this case, +1 +5. Here you have +3 +3. Here you have +3 +3. Again +3 +3. So you have possibilities of +3. So these are, so here they are A2+, B4+ O3. This is an example of A1+, B5+ O3. These are all examples of A3+, B3+ O3. Okay. You can also make mixed perovskites, such as mixture of, so these are mixed, let's say mixed perovskites, basically solid solutions. So mixed perovskites will be A2+, let's say B1/3 1+, 2+, and B1. So this is B1, okay. Then you have B2, 2/3 5+ O3. So for example, you have lead magnesium niobate. They are put in such a fashion so that the stoichiometry is maintained and the charge neutrality is there. So bismuth is 2+, you can only put 1/3. B1 is 2+, you can put only 1/3. B2 is 5+, it is strained to 2/3. So magnesium 1/3, niobium 2/3 will give you 4+ valence together. Okay. Similarly, you can have A2+, B3+ half, B1, then another B2, you can take half as 5+ O3. So this is, for example, lead scandium tantalate. Okay. So these are certain examples of perovskites. So we will finish here in this class, where we looked at spinel structure and perovskite structures. We will do the remaining structures in the next lecture. Okay.